Okay, so our last module for regression is predicted values and functional forms of regression. Our first learning outcome statement asks us to calculate and interpret the value of a dependent variable and to be able to create confidence intervals around it. Okay, so predicted values for our dependent variable. So essentially these are going to be the values our dependent variable gives using our line of best fit. And of course, remember our line of best fit is our estimated regression coefficients. Okay, so in other words, we take a predicted value of the independent variable, plug it into our formula for a straight line, and there's our formula for a straight line. Forecast value of the dependent variable is equal to the intercept plus the slope coefficient times the forecast value of the independent variable. Of course, error term missing there. Why is the error term missing? Number one, it's random, so you can't forecast it. Number two, it has an expected value of 0, so your best forecast would be 0 anyway. Okay, so let's dive in straight away to an example. So we've got our intercept and we're using the ABC example again. So we've been given our intercept here of minus 2.3 and our slope coefficient, and remember that's a sample value, comes from our regression, both the intercept and the slope coefficient are sample values, 0.64. And we're told that the market's excess return is forecast to be 10%. What is the predicted ABC's excess return according to the regression model? Well, all we need to do is say, okay, minus 2.3%, there's our estimated intercept value, or our sample intercept value, plus our slope coefficient, again, a sample value, times the predicted market excess return of 10%, and we get a value of 4.1%. Now, I think it's worth pointing out, really, there are two sources of error in our predicted value. Number one, we're missing the error term. Well, remember, the error term is random. We assume it's normally distributed with an expected value of 0. So again, we're missing the error term, but we wouldn't be able to predict it anyway. But the other major source of error when we're doing this is these two values here. These are sample values. In other words, they've come from our sample of historic returns that we used for our regression analysis. They're not true population values. So two sources of error really in a prediction: the missing error term and the fact that the intercept and the slope coefficient are sample values, not true population values. What this all means is we should really be creating a confidence interval around our forecast value. So we've got a forecast value of 4.1% and we're going to create a confidence interval around it. So a confidence interval, it's a prediction interval around a predicted value in which we believe with a degree of confidence the true population value would lie. Now, standard error of the estimate, of course. Now, standard error of the estimate, we already know what it is. It's the standard deviation of the error term around the forecasted values. So an estimated regression does not describe the relationship between the dependent and independent variables perfectly. We know there is an error term. And the standard error of the estimate is the standard deviation of that error term. It's not standard deviation around mean, remember. It's standard deviation around forecast value. So when we're creating a confidence interval, what we're going to use is the standard error of the forecast. Now, standard error of the forecast is designed to pick up on both sources of error. In other words, one, the missing error term. Two, the fact that we're using sample values for the intercept and slope coefficients rather than the population value. So what we use is something called standard error of the forecast. Now you can see the standard error of the forecast, well actually this is the standard error of the forecast squared here. It is a function of the standard error of the estimate squared. And what is the standard error of the estimate squared? Mean square error. Okay, so that is the mean square error if we're going to square it, of course. And then notice it's multiplied by 1 plus 1 over n, the number of paired observations, plus the variation in the independent variable, in other words, x minus x bar squared, over n minus 1 times the variance of the independent variable. Now, I think the chances of you actually having to calculate the standard error of the forecast from first principles, i.e. using this rather horrific looking formula here, are very, very slim indeed. I think it's far more likely that the examiner is going to give you the standard error of the forecast, okay, and you just have to create the confidence interval. But what you should know is that as n, and n appears twice here and here, as n increases, then of course sampling error. Oops. See if I can spell. Sampling error decreases. And remember what sampling error is from previous modules. It's the difference between a statistic and the true population value. So in other words, as n gets bigger and bigger and bigger, what we're going to find is that this bracket gets closer and closer to 1. So as n gets greater, sampling error is disappearing, and therefore this bracket gets closer and closer to 1. Remember, we said there were 2 sources of error that the standard error of the forecast was trying to pick up on. 1, the fact that we couldn't predict the error term. 2, that we were using sample values for the coefficients rather than population values. So as the sample size gets bigger and bigger and bigger, that second problem, the fact that we're using sample values rather than true population values for intercept and slope coefficient, gets smaller and smaller and smaller. So we are left with standard error of the estimate for very large samples. Because with very large samples, our major issue is the missing error term rather than sampling error. Okay, so let's get into an example of this. Calculate a 95% confidence interval for the predicted value of the dependent variable given an excess return of 10%, market excess return of 10%, so that's our independent value, and a standard error of the forecast of 3.67. Well, we've already calculated our forecast value and we said that that was 4.1%. But what we're now going to do is we're going to go a critical value times the SEF. So this is our critical value. It comes from a student's t distribution. And as per the previous slide, I'll just dance back to the previous slide. Okay, we are using a t-table with n minus k minus 1 degrees of freedom. Again, we've only got one independent variable at level 1, so it's n minus 2 degrees of freedom. So we should be able to look up that 2.03 by using a t distribution. We're doing 95% confidence, so we've got 2.5% in either of our tails. Let's find a student's t distribution. Here it is. Student's t distribution, significance 5%, of course. So there's my significance, 5%. 36 observations minus 2 gives us 34 observations. So you can see that we are somewhere between 2.042 and 2.021. Okay, so that is where they've got their 2.03 from here. They've obviously got a more accurate set of tables to get 2.03. 3.67 is the standard error of the forecast. We're going to give that just the notation SF. Okay, and there it is, 3.6. And that gives us a value of minus 3.4 to 11.6%. Okay, so we are 95% certain that the true population value of the dependent variable would lie between minus 3.4 to positive 11.6%. Again, if you want to think of that as a t distribution, oops, sorry, let me just do that again. There's my t distribution. There is my predicted value of 4.1%. We're going 2.03 standard errors of the forecast in either direction to capture 95% of observations. And that means the minimum tail or the lower tail starts at minus 3.4 and the upper tail starts at 11.6. So we are 95% certain that the true population value for the dependent variable would lie between minus 3.4 and positive 11.6. Right, last little bit, functional forms here. When the relationship between your dependent and independent variable is not linear, okay, so not a straight line, we have a problem in regression because linear regression, which is what we've been doing, ordinary least squares, linear regression, is all about fitting straight lines between the dependent and independent variable. So the problem is, if you fit a straight line to a relationship that is not a straight line, we're going to end up with biased predictions. Okay, we're also going to end up with serial correlation and heteroscedasticity in our error terms. But also, it's a bit more fundamental than that. You know, if you're trying to estimate a curve, so maybe here's our relationship between our dependent and independent, and it's doing something like that. Okay, then if you try and approximate it with a straight line and then forecast with that straight line, you're going to get useless biased predictions. Okay. So what can we do with this? Now, often we find a little kind of exponential curve like this when we have some form of constant growth. And if the issue is caused by constant growth, okay, we can actually get around the problem by what we call transforming one of our variables. Okay, so for example, let me just get up a white screen for a second. Let's imagine we're looking at a trend model and we've got time on this axis and we've got GDP in dollars on this axis. Now GDP tends to grow at about 3 to 4% per annum, doesn't it? So what that means in dollar terms, the change would be getting bigger and bigger and bigger each period. In other words, we would be seeing something like that, which is no good if we're going to try and predict it with a straight line. So what do? What we might do is try and transform our data, because what we might find is by taking the natural logarithm of dollar GDP, so we now change this to ln GDP. And remember, your natural logarithm, you do have it on the calculator. There's the calculator. If you look next to the number 7, you can see ln there for the natural logarithm. What you might find is when you take the natural logarithm, let's get rid of our curve. There it is, gone. You might find that you've then got a nice linear relationship that can be modelled. Okay, so lots of things that we actually model in finance grow at constant rates. So for example, interest in a bank account, if it's earning a constant rate of interest, then the amount of interest due to reinvestment is going to get bigger and bigger and bigger each period. It's growing at a constant rate. Lots of things do. Market capitalizations tend overall to grow at constant rates. So anytime we've got some kind of constant growth, we are going to need to transform our data. So what kind of models have we got? We've got a log-lin model. So a log-lin model means, just like we just did on that whiteboard, what we're going to do is we're going to take the natural logarithm of our y variable, our independent variable. Come on, pen. So we do ln y is equal to b0 plus b1 times xi. Okay, plus, of course, an error term. So that would be a log-lin model because we're taking the log of the dependent variable. Now, of course, what we might be finding is that actually it's our independent variable that is growing at a constant rate. Okay, so maybe we've got some kind of model and our independent variable is market capitalization, for example. So because that market capitalization of a company is growing at roughly a constant rate, we might want to transform that data. So this time we say, with our second one, we say, okay, the dependent variable is equal to b0 plus b1, and we take the natural log of the independent variable plus an error term. And that's a lin-log model. So log-lin if it's the dependent variable, lin-log if it's the independent variable, and log-log if we are transforming both. So there is constant growth in both the dependent and independent variables. So a log-log would look like the natural log of the dependent variable is equal to b0 plus b1 times the natural log of the independent variable plus an error term. That would be a log-log model. So just be aware that if you have a curve, because it's caused by, in particular, because it's caused by something growing at a constant rate, then often we can make it linear by taking the natural log of that variable. Okay? Is it always going to work? Is it always going to turn curves into straight lines? No, it might make the relationship between the transformed variables linear, in particular if the fact that it's not linear is caused by constant growth. Okay, so just be a little bit aware of that with your functional forms.